Okay, hello everyone. Thank you for joining. Today we have a remote speaker, Jazim Hussein. I hope I pronounced it correctly. He's on leave from Reed College and will be back there in a few months in the fall. He's now physically in India, so thank you for doing this at such a local, late time in the day. We do appreciate it. So Jazim has been working on a project to look for additional planets in the systems where TESS already detected candidates, and yeah, let's get going. You can take it away.
Well, thank you, Dr. for the introduction. Good afternoon, everybody. My name is Muhammad Jassim Munawar Hussain. I'm a rising senior physics major at Reed College. It's my pleasure to give my very first TESS science talk titled Looking for Multiplanet Systems Among TESS Objects of Interest. In this talk, I'm hoping to walk you through the extensive work that I've done over the last 11 months under the excellent mentorship of Dr. Michelle Kunamoto. And this is my first ever TESS science talk, or professional science talk for that matter. So I approach it with nervous excitement, and I hope you enjoy what I have in store today. So with that being said, let us move to discussing about the structure of this presentation. So I'm a big proponent for simplicity, be it even in a conversation with a friend or a topic I'm struggling with at school. I always try and find these simple questions I can sort of land back on and build, answering which I could build back to the level of complexity I'm expected. Being mindful of this liking for simplicity is how I devised the structure for this presentation. As you can see, I have found three questions, I may say almost linearly independent questions, answering which would allow me to elucidate better on what exactly I mean when I say we're looking for multiplanet systems among TESS objects of interest. The three questions, as mentioned here, are the why, the what, and then what. These are the three parts I've structured this presentation into, and we shall kick off with answering the first one. So let's answer the why question, the big why. Why should we be studying multiplanet systems? Well, as of today, there are 896 multiplanet systems known. And in studying about the different planetary parameters of their planets, such as their radii, masses, and also the orbital, their orbital parameters, such as their orbital history, their orbital arrangement, we can come to refine and redefine the model of planetary formation we've come to devise for these systems. This is also greatly aided by the discovery of new multiplanet systems, because we can use these new systems to check if our old theories, if these new systems conform to our known theories or suggest something different. Secondly, given the varied set of multiplanet systems that we do know about, it would be helpful to study about the planets which exist in the habitable zone of these systems. We could study about their atmospheric composition using transmission spectroscopy and emission spectroscopy. We could also detect signatures, biosignatures, if I'm not mistaken. All of which can be helpful in answering a rather philosophical question of whether there is life out in the observable universe. Finally, the study of multiplanet systems helps us in advancing a very niche field in the field of exoplanet science, the field of comparative exoplanetology. This field concerns itself with studying about how two planets which would have formed under similar conditions can yet turn out to be so different in terms of their physical parameters and their atmospheric compositions. Once again, the field of comparative exoplanetology is also aided greatly by the discovery of new multiplanet systems with time. as it allows us to, it gives us a bigger census of multi-planet systems to deal with and perform these comparative studies. So now that we've sort of motivated why multi-planet systems are of interest and why they're interesting, let's move to answering the second big question, the second part of this presentation, the what question. The what question, I think, could be answered more efficiently by dividing it into three different what questions. The first one would be, given the context that now we've set on multi-planet systems and why they're interesting, what have we resolved to do? Secondly, what were the different processes involved, given that we've set a certain research goal? That was the resolution. And finally, what kind of steps did we take to analyze the findings from our research project? As always, we begin with answering the first question, the one regarding our resolution. So to sort of put things first, our resolution was to contribute to the growing census of multi-planet systems. So we decided to search for multi-planet systems. However, I want to back up here and build a certain background leading to what exactly we mean by doing this specifically. Now, multi-planet searches have been performed from data from other satellites, for example, Kepler. But as for TESS, our satellite, the Transiting Exoplanet Survey Satellite, our spacecraft of interest, multi-planet searches have been predominantly performed using two main pipelines. The one developed by the SPOC team at NASA, the SPOC pipeline, and the other one, the Quick Look pipeline, developed at MIT with the QLP conducting multi-planet searches in the last 3 years. Similar to the format that was followed for Kepler, any planet candidate for that matter is uploaded to the TESS Objects of Interest catalog, first as a community TESS Object of Interest, and then it gets promoted to the status of a TOI. And this TESS Objects of Interest catalog is publicly available in the ExoFOM website. I want to sort of give a visual representation while I sort of try and compare the different pipelines that are used to deal with TESS data. As you can see, I guess TESS feeds its data to these different pipelines. I want to first talk about the SPOC pipeline. The SPOC pipeline uses target pixel files to analyze the brightness variations of about 20,000 stars of astrophysical interest. Need not be of interest to the exoplanet community, but however, 20,000 stars every sector. This data has a 2-minute cadence rate. And the good thing about the SPOC pipeline is that it conducts a multi-planet search by default. So it's already done. On the other hand, we look at the QLP pipeline. This one accesses TESS Full-Frame Images, which contain millions of stars. And currently, the cadence rate is of about 200 seconds. Due to limited resources, obviously, the QLP pipeline searches specifically for planets or stars brighter than 10.5 mag. And I finally want to get to the QLP faint star search pipeline. This pipeline is an extension of the existing QLP pipeline. It does use QLP-processed light curves and searches for planets for stars with a brightness in between 10.5 mag and 13.5 mag. And it does not search for multi-planet systems. I'd also like to point out that the QLP faint star search pipeline has contributed to about half of the known TOIs right now. And as the process goes, for all these different pipelines, the promising planet candidates are all uploaded to the TESS Objects of Interest catalog. Now, I want to sort of make one observation here. In the QLP faint star search pipeline, we see that multi-planet systems are not searched for these relatively dimmer stars that are not searched by QLP. And we also noted that the QLP pipeline had begun a multi-planet search within only the last 3 years. This suggests that an improvement can be made to make a targeted search for multi-planet systems. But before we get there, I want to point out a rather interesting phenomenon. So it turns out planets within multi-planet systems have a lower false positive rate when compared to planets that exist in single transiting systems. This trend was also observed in Kepler multi's data, and it is referred to as the multiplicity boost. Now, hang on a minute. What would this mean? Is it possible that we could leverage this multiplicity boost, given that we have an entire repository of TOIs in the TESS Objects of Interest catalog? It contains the planetary parameters, at least what is available, of every planet candidate TESS has ever observed. What if we could leverage this multiplicity boost and search for new systems, new planets in systems which are already known to host an exoplanet? This is the TOI catalog, and as you can see, it's got all the data that we would need. And that is exactly what we set out to do. So we decided to conduct a targeted search for new planets within existing planet systems which are known to host an exoplanet using the, or planet candidate using the TOI catalog. Pretty much laying into our mission statement of looking for multi-planet systems among TESS objects of interest. Now, sort of looking back at what we've answered in this part of the why question, we decided that we were going to contribute to a census and search for new multi-planet systems. And we've decided to leverage the multiplicity boost that is known and look for new planets in systems which are already known to harbor a planet candidate. We now move to answer the second what question. So now that we've set a research goal, what kind of measures did we take to perform the research? Now, before I move to, and the second question can be very well answered by describing our search methodology. I'd like to take a second to look at our overarching search methodology and sort of lay a motivation before we get there. So as you can see here, our search methodology was pretty simple. We downloaded all the data we required from TESS. We recover all the known TESS objects of interest using a specific algorithm, and then we remove them so that we can use the residual light curve that remains and search for new transiting exoplanets. Now, with this background in mind, we move to exploring the actual search strategy. So, as a first step, we download the data of we download the light curve data from TESS using the light curve with a K package, and we stitch it together, make it ready for plotting that happens in the back. We chose specifically to work with data processed by the QLP pipeline rather than the SPOC pipeline, even though the SPOC has a lower cadence rate. And this was because the SPOC pipeline, however, does not have information on all TOIs, whereas the QLP processed light curves, we have information for pretty much every known TOI. As a second step, the light curve was plotted in the background as a preliminary step. Once that was done, we then performed a detrending process to remove the effects of stellar variability, giving us a cleaner light curve that the transits all in place using the by-weight time window slider in the Wotan package. All of this is in preparation for detecting the transits. And now we get to our transit least squares algorithm, the main part of this of answering this question. So there are two algorithms that are used in detecting transiting exoplanets: the box-fitting least squares algorithm, the BLS, and the transit least squares algorithm, the TLS. Our choice of using the transit least squares algorithm instead of the BLS algorithm came from the fact that TLS performs better fits that fit the shape of the transit better. Also, that TLS accounts for the activities of planetary ingress and egress that are present in a planet's transit. So it overall just gives us a better shape, leading us to choosing it over BLS. Before we speak about how TLS was applied in our search mechanism, I'd like to just go over a general approach of how TLS works. Firstly, given a light curve, it searches for the ideal period that can fit the given transits or the given transit-like activity we see in the light curve. Secondly, once the ideal period is determined, it fits the transit, as you can see here, and also as in the second plot, it's sort of red in color, so the transit curve is fitted, and also in the background, a set of transit-related parameters such as the orbital period, the transit depth, TLS computed signal-to-noise ratio is all calculated in the background. Using this, we now identify all the points in transit as a third step, and remove these points in transit as we continue in the process of looking for new systems. So how did we use the TLS to conduct our multi-planet search? Now, like I said, the first goal is so let's take a star, target star. The first goal would be to remove all of its associated TOIs. Now, we have the information of the periods already. So we searched for the ideal period by setting it within 10% of the known period of the known TOI. So this means, and our reason for just not searching using the period already known and searching within 10% of the known period was because of the fact that some of these TOIs, ever since they were promoted, have not been looked at for a while. And by expanding the area, the threshold through which it is searched, we were able to get an updated set of ephemerides. Now that we've recovered the known TOIs transit fit, we look at the points in transit and then we effectively mask it out, or in other words, just remove those points. And once again, perform the same process to recover any additional known TOI. Now, this process is repeated until every known TOI is recovered. And once we're done with that, we move to the actual multi-planet search. And we choose to call it the blind search. So now that we have the residuals in the light curve, which does not contain any of the transit dips from the old TOIs, we now perform a TLS run again, searching for up to 3 additional candidates. This was done for every host star that hosts TOIs. Once this blind search, a pretty computationally time-consuming part of our planet search, we hand over every signal that has a TLS computed signal-to-noise ratio of greater than 10 through our automatic vetter LEO, which is short for lazy exoplanet operations. Now, LEO performs tests to compute astrophysical false positives, such as eclipsing binaries, and false alarms, such as systematics and noise, by looking for sinusoidal variations, a significant difference in depth when looking at the odd and even transits, and also uses difference images to check if the targets we're looking for are on or off target. So LEO does its automatic vetting process and classifies every interesting signal with an SNR above 10 into either false positive, false alarm, or a planet candidate. So that's how they're categorized. This is a sample vetting report that is prepared by LEO. Actually, it's not even a sample. This vetting report is for the TIC 3023050.02, one of our candidates, and my personal favorite for reasons I shall get to in a couple of minutes. As we can see here, the LEO vetting report contains the raw flux, the trended flux, the overall phase diagram, a phase diagram focused on the transit, the odd and even transits, the most significant secondary dip that can be viewed, and the phase diagram for half the orbital period. We also see that it contains the individual transit curves, as we can see here. And the LEO report also contains the pixel level images. And if you can see the second row, the goal for us would be to check if the little star is present in the box or in the pixel which has the most brightness, which is the case over here. That indicates that our candidate is on target. The LEO vetting report also contains a few planetary parameters that are useful. And all of this information actually is useful for our next and final step in this process, which would be manual inspection. So we look at the vetting report produced by our automatic vetter and check to see anything that has passed with the planet candidate classification, if things check out. And in our inspection revealed the discovery of 7 new candidates, all of which, upon confirmation, confirm the existence of 7 new multi-planet systems observed by TESS. So with this process, we've answered the question of what kind of efforts did we take now that our research goals were set. So we used data from the TOP to search for transits. We applied the transit, we applied a detrending measure, and then once our data was ready, we used TLS to search for our known TOIs. We removed them, conducted a blind search to recover our new exoplanet candidates, and then put it through an automatic vetting process, which is then followed by a manual inspection process, giving us 7 candidates. We now move to the next step, which is, now that we know we've got 7 new planet candidates, what kind of measures did we take to analyze their data? Now, firstly, for planet candidates which have a radius that is smaller than 6 times Earth radius, we performed what we call a false positive, it is called that way, the false positive probability and the nearby false positive probability using the Triceratops package. And a point I'd like for all of us to note is that the reason we excluded 2 candidates which had a radius higher than this threshold of, 6 Earth radii is that larger objects using the transit method are indistinguishable from brown dwarfs. So that's the reason we excluded them from this calculation. Now, while the calculation of false positive probability can be used as a statistical measure, we did not make these calculations to claim statistical validity. Rather, we did these calculations to sort of imply the confidence we have in these candidates. That is, a low false positive probability would imply a higher level of confidence that we have in our candidates. So also, we'd like to note that a nearby false positive probability of 0 for all of these candidates implies that all of these candidates are indeed on target. As a second data analysis measure, we fitted transit models for all our new candidates using the exoplanet package, using a 2-planet transit fitting routine, arriving at a posterior distribution of several useful planetary parameters. And we take the mean out of that to arrive at our accurate planetary parameters, which I present forward in this table. I'm going to give us about 20 seconds for us to just take a quick look at these candidates in silence, and I will resume right after that.
I thought you were ignoring large planets.
I'm sorry, I couldn't understand that.
You mentioned you're excluding R/6 Earth radius, right?
Yes, that was for the false positive probability calculations, not for the transit model fits. Sorry if I forgot to mention that. So the transit model fits were for all fits.
Okay.
So with that, we conclude the answering of the what section. We've effectively answered what we've done now that we know that we have 7 new candidates. We've got their updated planet parameters, and now it's time for some fun, actually. The then what section. So now that we have 7 new candidates to discuss about, are there any interesting systems that we have here? Do they not conform to any new trends that should be mentioned about? These are all very valid questions, which is what we will explore in the then what section. The first one that we decide to look for is orbital resonances. So to check if any of our planet candidate pairs were in mean motion resonances with their companions, we calculated the normalized distance to resonance, delta in this case, using the formula presented here. And a delta value close to 0 represents a near resonant pair of planets. Now, why do we choose to study about to check for the existence of any mean motion resonances? To have planets in an orbital period ratio of whole numbers indicates an interesting dynamic relationship between them. And also it warrants a transit timing variation analysis to check if that exists, because this could be used to confirm the existence of our candidates. And in our case, we did strike orbital mean motion resonance. So our candidate, CTOI 4059035.02, along with its big brother, TOI 2037.01, displayed an orbital resonance of ratio of 2:1. with a very low distance resonance of 0.00521. So we're hoping to check if there is any transit timing variations for this particular planet pair as part of our project in the days to come. Moving on, I'd like to talk about an interesting 5-planet system that we have as part of our study. So the TIC 53498154 system, at the time of our start, had only one known planet candidate. It was a super Earth with a period of about 13.7 days and a radius of about 3.38 Earth radii. We detected using our pipeline an additional inner candidate, a super Earth, with the CDOI as mentioned there, in a 3.386-day orbit with a radius of about 2.207 Earth radii. However, in the months that followed, we saw that this system had a few more additions. Precisely 3 more planet candidates that was observed using that was followed up using KOPS, the KOPS team. And I'd like to point out that the 0.05 planet candidate is an outer transiting single transit candidate. Now, the good news as far as this system is concerned is that 4 of these candidates that were already known, including the innermost transiting CTOI, have all been promoted to the status of TESS Object of Interest a couple of weeks ago, highlighting the success of our project and giving us a rather interesting system to deal with if the 5th planet also confirmed as well. It joins, I think, an exclusive set of 30-odd known multi-planet systems which have 5 transiting planets. We now move to TOI 5487 system, my personal favorite among all of these discoveries. So in this case, we have an extremely rare case of a hot Jupiter accompanied by a close-in giant planet. So the first candidate in the system, the previously known TOI, which we used, was a hot Jupiter with an orbital period of about 4.6 days and a radius of about 9.187 Earth radii. Our investigation revealed the existence of an additional close-in outer candidate, TOI 302305400.02, which had a 15.797-day orbit and a radius of about 10.35 Earth radii. I'd like to also point out that there are only 21 known single star systems where a hot Jupiter is even known to have a companion. So given this context that we've set, I'd like to go back to a little bit of background until before we arrive at our conclusion as to why this system is particularly interesting. So hot Jupiters generally were known to not have many companions, or any companions for that matter. And this, they were expected to be quote unquote lonely, resulting from a planet formation model that it would involve a dynamically violent process, such as planet-planet scattering, leaving hot Jupiters isolated and closer to stars. However, in the recent years, with the discovery of companions to the WASP-47 system, the TOI 1130 system, the Kepler 730 system, we found close-in companions to Jupiters, which challenge these dynamically violent theories of hot Jupiter system formations. This has allowed us to rather suggest a less violent formation mechanism, such as in situ formation, or a migration mechanism such as quiescent disk migration for these systems. However, I'd like to point out that for all of the companions, the close-in companions for hot Jupiters, for these hot Jupiter systems, none of the companions had a radius that was larger than the typical maximum limit for a mini Neptune, which would be of about 4 Earth radii. None of them crossed that threshold. So, given that I also did a little bit searching about this, we've come to conclude that there is currently no known hot Jupiter system where a hot Jupiter is accompanied by a close-in outer giant companion, which would mean that TOI 5487 system would be the first ever system where we witness a case like this. Hence, I mean, pretty self-explanatory as to why it is my favorite. I also would like to present an alternate case here, which we're cognizant of. So given that using the transit method, we deal with radii as large as 10 Earth radius, it is possible that what we look at currently as a planet candidate might as well be a brown dwarf. So we recognize that, we're cognizant of that, and we think that this pretty much warrants a radial velocity analysis, which could give us the mass, which would make it very easy to recognize if this is a brown dwarf in this case, or a transiting giant, which would be pretty awesome. We now move to our assessment of the follow-up potential for our candidates. Now, we assess the follow-up potential for our candidates for two specific follow-up methods: radial velocity follow-up and atmospheric characterization follow-up. Now, to assess which of our candidates were viable for RV follow-up, we calculated their radial velocity semi-amplitude using this formula presented here. Now, I would like to point out that the mass of the planet mentioned here was an estimation that was calculated using the mass-radius relationship that was provided in the paper that we used in this case. To determine candidates suitable for transmission spectroscopy, the atmospheric characterization, we calculated the transmission metric, that is the TSM values, using the formula provided in the Kempton paper 2018. Once again, as you can note, the mass of the planet is determined using the mass, is estimated using the mass-radius relationship mentioned in the paper. With that, we have the calculated values. You present the calculated values for both the RV semi-amplitudes and the TSM values in this table. Now, first, choosing to focus on the radial velocity semi-amplitudes. Instruments worldwide have a sensitivity, a minimum sensitivity of 1 meters per second to be for a radial velocity follow-up. And I'd like to point out that all of our candidates cross this threshold, and particularly CTOI 302305400.02, my favorite possible close-in giant companion to a hot Jupiter, has a RV semi-amplitude of about 19, not only indicating how significant this system is in warranting a follow-up, but also how viable it is in the case of radial velocity follow-up. Now, observing the TSM calculations, as mentioned in the Kempton paper, for planets with a radius in between 1.5 Earth radius and 10 Earth radius, a TSM value above 90 would be favorable to wouldn't necessitate, but qualify the planets for atmospheric characterization. Unfortunately, that is not the case here. However, these are all interesting candidates that are present in multi-planet systems, which already increases their chances of being valid given the multiplicity boost, and can all very well be used for performing comparative studies in the future. We now move to the final part of our analysis of the interesting trends we can find in our system and comparison to other systems. So we chose to sort of check for a common size trend that we know in multi-planet systems. We know that mini Neptunes and super Earths are amongst most commonly found types of exoplanets. So to check this, we lined up our the radii of all of our candidates, and we find out that 5 of our 7 candidates have a radius that falls within the range typical for mini Neptunes, which indicates a general conformity to this trend. The notable exceptions, the two candidates mentioned here, they have a radii of about 6 Earth radius and 10 Earth radius. They qualify as gas giants. But once again, we pretty much see a general conformity here, nothing out of what we expected. We owe a great deal of gratitude to the Kepler mission. It has provided us with very valuable information on compact multi-planet systems. And given the plethora of information available, we wanted to make a comparison of our new possible multi-planet system to the typical systems observed by the Kepler telescope. To do this, we used data used by the California Kepler survey, who studied 365 multi-planet systems and published a set of overarching trends that were present in them. So we're going to be checking some of those trends for our candidates and see whether they conform to them or present a conflicting opinion. The first trend observed in the California Kepler survey, CKS, was peas in a pod. So a planet in a multi-planet system was likely to be the size of its neighbor. And not only that, it was the inner transiting planet for a system was smaller than the outer planet for the system in 65% of planet pairs. So to analyze this, we calculated the size ratios between the inner and the outer candidate for all our systems, first and second candidates in terms of distance from their star. And our calculations reveal a mean of 0.89 and a standard deviation of about 0.13, moderate deviation there. But this implies that about on average, the inner planet is 89.4% the size of its outer neighbor. So it does conform to what was observed in the CKS trend to a very reasonable extent. As for the second statement made here, we see that 6 of our systems have an inner planet with a radius smaller than its outer companion. The only exception is found in the TOI 2037 system, where the outer candidate was larger by the inner known TOI. Where the inner candidate was larger than the outer known TOI by a mere 7% of their radius. The next trend that we did analyze is a lack of ultra-close planet pairs. So Kepler planet pairs with a radius range of 0.5 and 4 Earth radii, they were observed to have an orbital period ratio larger than or equal to 1.2, but never lesser than that. Now to check if this trend was followed in our candidate systems, we determined the orbital ratios for the first and second most candidates as far as distance from the star is concerned. And our calculations revealed a full conformity to this known trend. In fact, the lowest orbital period ratio observed was 2.19 in our case. This points to a possible common formation mechanism for these compact multi-planet systems that prevents these planets from getting too close to each other. But that would be a question or a hypothesis that can be answered outside the scope of this project. So I'll sort of leave it there. The final CKS trend was that we chose to analyze was that smaller planets tend to have smaller orbital period ratios. Now, to do this, we took the average planet sizes for the 2 planets that we're dealing with in our systems and viewed their orbital period ratios when approaching the average planet sizes in a descending order. And in doing so, we found out that the smaller average planet size corresponded to a smaller orbital period ratio 4 out of 6 times, once again, indicating a conformity to this known trend as well, a very good general conformity. So rounding things up, we see that for our new candidate multi-planet systems, they generally see all the trend that is known for multi-planet systems in general, and also for the compact multi-planet systems that were studied in the California Kepler survey. With that, we move to the conclusion of this TESS science topic. In this project, we conducted a targeted multi-planet search among subjects of interest using the TOI catalog. We performed a TLS-based search, followed by automatic vetting and manual inspection, leading to discovering 7 new planet candidates, which all of which upon confirmation will confirm just as many new multi-planet systems. All of our candidates have an RV semi-amplitude value high enough to be detected by standard instruments worldwide. Moving to interesting systems, one of our candidates, CTOI 53498154154.02, is a member of a 5-planet system and has now been officially recognized as a TESS Object of Interest. CTOI 405559035.02, that displayed a orbital resonance ratio of 2:1 with its companion TOI, hinting at a rather interesting dynamic history with its companion and also warranting a TTV follow-up. And finally, the CTOI 302305400.02 is a candidate which, if confirmed, would present a very significant discovery to the exoplanet community, as it would be the first ever known giant close-in companion to a hot Jupiter. And on that note, I would like to thank you all for listening to this talk, and would yield all of my remaining time for questions, comments, or anything along those lines. Thank you.
Thank you. Very well-structured, thoroughly structured, and well-delivered talk. Let's open it up for questions. If anyone wants to ask a question online, you can raise your hand or just unmute and go ahead. Anyone in the room?
There was a statement early in the talk that multi-planet systems are less likely to be false positives. Why is that?
That is an interesting question. In preparation for the talk and writing my paper, I did not go into the specifics of what the cause is, but I'd like to sort of inform that this was observed in Kepler systems, in studies that was conducted on Kepler multi-planet systems. So while I don't have a specific answer as to why that is, I would be happy to revert back with the answer.
I'd like to weigh in.
Oh, so essentially, because Kepler studies found that if there was, like, most planets existed in multi-planet systems, and by doing through statistical validation, you can show that they're more likely to be real. Like, if you have multiple transiting objects around the same star, it's unlikely that it's like an eclipsing binary causing all of them, right? You'd need an astrophysical false positive to just explain all of them. So multi-planet systems are going to be less likely to be false positives. And so that's what's known as the multiplicity boost. I don't remember the exact number about how much more likely it is for a multi-planet system, for planets in multi-planet systems to be planets, but it's typically incorporated in statistical validation practices when you're confirming multi-planet systems that they're 100 times more likely.
There was a paper by Jack Lissauer
Yeah.
from 10 years ago-ish that completely goes into all the details of everything you want to know about that. He went.
Does it compare?
He's still talking about it a lot. If you ever meet him, and
what does it compare against the odds of like having two nearby eclipsing binaries because they have
Exactly.
the same source?
the short story, the short way to say it is there are many false positive scenarios that can explain a single transiting planet false positive. There are hardly any that can explain 2 or 3 or 4 transiting signals in the same light curve where all of them are false positive. All the transit signal, all the individuals are false positive. It's very difficult to come up with such a scenario. You need fine-tuning of many things. That's hand waving, of course, but we can do it in a more quantitative way.
Well, we also have a question in the chat as to what needs to be confirmed on the one close-in Jupiter system.
Yeah, I was wondering about that too.
Okay, so the confirmation can be done, to confirm if this is actually a planet. So what we're trying to confirm is that if this is a planet or a brown dwarf. Now, this can be done by calculating the mass, which can be done in a radial velocity follow-up. And when we do have the mass, we can see if it is typical for a planet or typical for a star. It would clearly point out if this is a very, very, very rare discovery or just a brown dwarf that we all thought was exciting.
A brown dwarf in that system will also be extremely rare and maybe difficult to have dynamically.
Okay, wait. So
dwarfs are in general there. In general, regardless of whether there is another planet in the system or not, but also dynamically, and you can weigh it. Having a brown dwarf in the same system with another giant planet, dynamically it's very difficult to keep the system alive.
Yeah, so radial velocity follow will definitely help distinguish between either scenario, but also being able to confirm that these are indeed on target. So we do have the difference images and the nearby false positive probabilities that both indicate that it's on target, but we would need follow-up, like ground-based photometric follow-up to be absolutely sure about that.
But if you follow up by RVs, you get a minimum mass, right? There's still regenerative perspective.
No, there's no chance, I think.
Oh, sorry. Actually forgetting. I've been working in RV detection so long. Yeah, transiting stuff.
Nobody heard that. Just recorded, but that's it. Yeah, I'll personally be curious to see what happens with that system, and we can also talk about it a bit offline. How do we push forward the follow-up with that one? More questions?
I had one.
Yeah, go ahead.
I was sort of curious how many signals went into Leo and came out. Well, I know how many came out. How many went into Leo after the TLS search?
That's a good question. Part of my work was actually more associated with the pipeline. So I'm aware that the number of signals that came out of Leo initially were 9, and then using our by manual inspection we brought it down to 7. But I'm not sure the number of signals that went into Leo. I think my supervisor dealt with that part of the project, so perhaps they have an answer.
I don't remember the exact number, but
Order of magnitude.
it would have been, on average, every TOI would have had one, like every TOI had one signal, so about 6,000 signals.
Okay.
Oh,
But
and
the
only
vast majority were
order of
false
10
alarms.
went out.
Yeah.
Okay, that's a big.
Okay. Yeah. Thanks.
That's big. Okay. Other questions? What about that 5-planet candidates system? Are you trying to push on that specifically?
Actually, I spoke to the person who uploaded the other 4 candidates, and he informed me that we can expect a characterization paper to come along. They also have a year of HARPS N observation that could be used for radial velocity analysis.
Who is that? Do you remember the name?
Who is Hugh Osborne
Ah, okay.
at the University of Bern. He used to be at Kavli before.
Yeah, I think now he's at
University of
Bern
Bern.
in Switzerland, Bern University or University of Bern.
I see another question in the chat. Did we take out known false positives for running our analysis? Well, the false positives, if I'm not mistaken, were identified by Leo. So I remember having an eclipsing binary and getting very excited about it, and then we used Leo. I used Leo to find out for that individual candidate, and it was not the case. So we didn't really remove anything for running the analysis. It was in the analysis that false positives were weeded out automatically in the process. I hope that answers the question.
Pam, does that answer the question?
Yeah, I was really wondering because when we do the light curve vetting, there are a number of TOIs and the number keeps increasing that have been designated by ExoFOP as false positives that might have secondaries. And it was really just wanting to know if you took out those before doing it or if you included them in it and therefore possibly were catching the secondaries as well, if that makes sense. Yeah, because they're still TOIs, they're just known false positives.
Those would
Yeah.
show up. Well, I mean, you can go ahead.
No, I'll wait.
So sorry, Pam, are you talking about signals that would be false positives due to eclipsing binaries, and then there's additional signals that are due to their secondaries that could be picked up as unique candidates?
Yeah, I think that might be possible, because if there's a TOI that you know is a false positive from ExoFOP, you know, the work's been done there. You could always find another signal there that was a secondary, if that makes sense, especially if it's an eccentric secondary. So I was just wondering if you put absolutely all the TOIs in, or if you only put those in that were PC or APC, and not the
only
false
PC.
alarms and the FPs.
Yeah, we didn't search the false positives or the FAs, the false alarms. And any of the current PCs had secondaries, you would see it in the vetting report, because there'd be in the phase diagram a gap where the primaries would be, because it's at the same period.
The secondary of the secondary.
Right, so none of the candidates that we found would be the secondaries of possible ecliptic binaries that haven't been dispositioned in the TOI catalog.
Brilliant, thank you, Michelle.
Or in other words, the period will be a 1-to-1 ratio, which you'll notice.
Yeah, as long as you had all the events, because some of the longer period ones, you might get just you might be missing a primary or a secondary, and then you might, if you have relatively few events, you might think you've got a 2-to-1 ratio, which would be quite exciting.
That's something to keep an eye on.
Yeah.
Although most of those objects are not that short period, are not that long period, they're actually on the short side.
Yes, so
the scenario you mentioned, Pam, that happened to us over the years.
yeah,
and it can still happen in the future, but specifically for relatively long period objects where we catch only some of the transits.
yeah, we've seen a few of those in group vetting.
Yeah,
where
they
the
show up from
second,
time to time, and they will continue to show up probably. But
yeah, where the secondary was alerted because it was small enough, and yeah, it does sound a very interesting project, and the whole concept of finding these multi-planet systems does sound fascinating. So I'll be very interested in seeing what comes out of it in the long term.
Yeah, we're hoping to get a paper along in the next weeks, and hopefully submitting the paper along. So it should be after the peer review process. It should be hopefully by the end of summer. The paper should be out, highlighting and talking about these discoveries in detail.
yeah,
That'll be one to keep an eye on.
I'm sorry.
Any last remaining question? If not, then thank you again. And especially given the late hour, I think now I think you've done enough for the day. You really deserve a good night's sleep. And hope to see you in person in Cambridge in the near future, actually.
Of course, I'm looking forward to
and
that.
for everyone else, this is likely to be the last TESS Science talk for the semester and the year, but maybe we'll have a few more sometime during the summer. If any one of you want to present something, or if you have a colleague or friend that would like to present something, let me know. We can either do it sometime in the next few weeks or months, or schedule it for the beginning of next year in late August or early September. So thank you again for joining, and have a good rest of your day.
Cheers. Likewise.